So over here, we're going to go and draw two blocks of semiconductor over here, which is going to be material that has only got 4 valence electrons. Just mark that over here as being 4VE, 4 valence electrons. We've got two separate blocks of it, and then what we're going to do is we are going to go and dope them. And one of these sides is going to be trivalently doped, and the other side is going to go and be pentavalently doped. And these two terms, trivalent and pentavalent, are coming from the Latin roots, 3 and 5, which tells us that we are going to go and add in impurities that are going to be adding either 3 valence electrons or 5 valence electrons. Which means that in our base material here that had 4 valence electrons initially, now we have got mixes some impurities, so it's got less. In other words, it is going to go and have what we will refer to as holes inside of it. So just draw in 5 holes over here. On this side, we've got pentavalent, which has got 5 valence electrons, and because it's got the 5 valence electrons, we're adding that to the 4 valence electron base, which means that now we're going to go and have an excess of electrons that is going to go and be inside of here. So electrons we're just going to represent with dots, holes we'll just draw as being little circles through the remainder of electronics over here. We see that we have got these two materials. Once we place them together, we're going to go and get this little bit of a reaction that's going to happen right at this boundary layer. So right over here where these two materials are going to come together, we are going to go and have electrons that are going to flow from the side that's got an excess amount of electrons, this side, that are then going to go and flow over and fill a few holes on this side over here. Basically, our nearest ones to the junction are the ones that are going to go and move. So this one over here would move over there. These ones here that are further away just can't make it through the resistance of that semiconductor. Same with these ones over here, can't make it through the resistance of that semiconductor. So we're not going to get much current flow other than at this boundary area. And that little boundary area, we are then going to go and set up what's called a depletion region or a barrier voltage. Depletion region just means that we have gone and depleted the charge difference, the 3 and the 5, we've balanced them out to become 5. And a barrier voltage just refers to the fact that I've had an electron that has moved from here to here through here, which is going to go and give me a value of voltage. Anytime that an electron moves, if it's being forced by something, then that thing is going to be a load that we would have it moving through. But if it's through a reaction, like what we have over here, then it's going to be a source. So we know that current flows from positive to negative through the source, which would mean that this little side over here would have to be positive, this little side over here would have to be negative. And that creates a barrier voltage, which is just going to be a small voltage that's going to oppose anything else that happens in the circuit. That barrier voltage needs to be overcome before we're going to be able to go and establish current flow through our PN junction. And usually it's just going to require a small amount of voltage, anywhere from 0.5 volt up to 1 volt. We are going to say for silicon, it's going to require 0.7 of a volt. It's just a value we've used through the previous 2 years. We're going to use it through here as well. And for germanium, it's going to be 0.3 volts. That's the barrier voltage is all we're overcoming with that little voltage drop that we have. Okay, let's talk about what happens now when we connect this thing to a source. Well, let's start by designing a source over here. So I'm just going to remove all of this and all of this so that we can go and see 2 different sources over here. We'll just remove that as well and that as well. Yeah, we'll just remove all that. Perfect. So I'm going to go and draw out a battery up top over here. I'm going to have a battery that's going to be facing in this direction, and then over here on this side I'm going to go and have a battery facing the opposite direction. We're just going to go between these two. I'm going to have my positive side of the battery, which is going to be indicated by the big lines. I'm going to have my negative side by the little lines, same with over here and over here. Well, what is the positive side of a battery and what is the negative side of a battery? It's really referring to what has happened electrochemically inside of that battery. So we have taken a couple of different elements, we've combined them into compounds and mixtures in some cases, and then we go and place in some chemicals which are going to go and cause reactions inside of there. And there's a lot of chemistry, we're not going to get into that. Suffice it to say that there are going to be electrons inside of here. So we're going to have materials that have electrons, and the chemical reaction is going to go and rip electrons away. So right in here, there's unhappy little electrons that are going to be ripped away and stored over here at the negative pole of the battery. And because they've been ripped away by this chemical separation, that's going to leave us at the positive pole of the battery an equal amount of holes over there. See that? Sad electrons over here, here's their home. It's the mean bad chemical inside that has ripped them all away from there. And ultimately, all that ever happens when we connect a circuit from one side to the other is that those electrons are going to go and find their way back to the corresponding hole, and then the chemical is going to go rip them across the battery again. They're going to keep doing that circuit. That's a short-circuited battery, and it would keep doing that until the chemical compounds inside have, broken down or oxidized, and we have all these other things that happen inside of a battery. If we go and take this battery that we have drawn up top here, and we connect it over to here, and we take this side and we connect this over to here, what's going to go and happen? Well, let's start by examining what we are connecting to which. Let's go back to some fundamental rules that we have about electricity, magnetism, because all that stuff is so combined together, so intertwined, and that is that like charges are going to go and repel, and opposite charges are going to go and attract, whether that's for magnetism, north and south poles, or whether that is going to be for electric charges, positive and negatives. Over here, I see on the battery that I've got a whole pile of electrons over here that are being pushed out of this battery by that chemical that's on the inside. Okay, we'll just draw a big slimy chemical on the inside there. They're being pushed out, which means that we're going to go and have more electrons that are going to go and travel, bigger marker here, travel down this, and they're going to start to fill up inside of here. And as they fill up inside of here, they're going to be taking up more and more room. They're going to be pushing this barrier region smaller and smaller. And as they push it smaller and smaller, they're getting closer to this opposite side. Simultaneously, on the other side, we see that we've got all of these holes that have been created. Once again, because of my chemical reaction inside of there. So we are going to go and have more holes that are going to be generated on this side. The battery is actually going to be sucking electrons out and ripping them over to this side over here. So we start to generate more and more holes. And as we do that, we start to see that we're getting holes that are now getting closer and closer to this depletion region. And eventually what happens is that this depletion region itself is going to shrink down so small as my battery voltage, is increased, that I'm going to be able to now start pushing actual battery current through, flowing through from here. It's going to be able to go and overcome this barrier potential that I have over here, because the barrier potential is going to be so incredibly small. We've actually shrunk down this barrier potential because we have started to move electrons right here into this side that was balanced before, and we started to go and move holes into this side that was balanced here before. So we start moving those in, and now we're able to actually overcome that barrier potential and get mass current flow that is going to go and happen all the way across to my battery. Perfect. This is going to be us forward biasing a PN junction. So it's just a P-type material and an N-type material. This is what creates current flow. It's phenomenal. So when we forward bias a PN type of material, and the P is going to be my trivalent, and the N is going to be my pentavalent. That is going to go and give us this current flow that we're having through here now. So when we forward bias it, great, we get this full operation. What happens though is that we can reverse bias it, and we can have other strange things that are going to happen. So let's just go and take a look at what happens when we go into a reverse bias. We'll draw up that depletion region there again in a second. I just want to erase out all of these other little tiny electrons we placed inside there. Good. Okay, so let's take a look at what happens if we go and connect a battery in the opposite direction. If we connect in the opposite direction, we see that we have got holes over here. We see that we have got electrons that are over here. And what's going to happen when we go and connect like this with my negative to the P-type material and my positive to the pentavalent type material? Well, we see that all of these electrons, which we have an excess of, are going to go and see holes. And what happens when we get electrons and holes is that we are going to go and get those electrons that are going to go and flow out of here to go and fill those holes. And that depletion region, which was small in the beginning, in the area where we had balanced this thing down to 4 valence electrons, is now going to start to grow. It's going to start to move outward as we go and suck all those electrons out of that side over there. On this side of the battery, we are going to go and deliver a bunch of these electrons in, and as we deliver those electrons in, they're going to go and fill each of these holes over here, which is going to go and take this entire side of the battery. It's going to do the same thing. We're basically going to be moving our depletion region, making it larger, and this depletion region acts like an insulation. So at the instant that I connect it reverse polarity, there's going to be a brief little blip of current flow, and then after that, I'm going to go and have balancing, and there's going to be no further current flow because this depletion region is going to have basically filled out both sides of my PN type of materials. It's been reverse biased at that point, and that's really going to be the end of the current flow. We just get that one little blip, and after that, this whole thing acts as if it were an insulator. This fundamental item that we have drawn in over here is going to go and be our diode. And we've taken a look at this thing inside of first and second year. A diode, which we're commonly going to go and see drawn like that, which is going to go and tell me that this line over here is going to be my N type of material, and this line over here is going to be my P type of material, the arrowhead that we're going to go and have inside of here. Forward biasing and reverse biasing a diode works, to go and either give us current flow or to interrupt current flow. It becomes basically a one-way valve for current flow. As we saw in this, when we connected it with a positive to the P type and a negative to the N, we created a path for current flow. But when we go with a negative to the P and a positive to the N, then it goes and blocks. We took that diode, and then we took it and we added in another layer inside of first and second year as well, which was us adding in the third layer. It could either be PNP or NPN, where we were going to go and create what we refer to as our bipolar junction transistors, or the BJTs. And BJTs are just simply 3 blocks, and we'll just go and call this thing NPN over here, which means that I'm going to go and have one that is going to be pentavalently doped. Which one's pentavalently doped? Well, I hope you said the N. Okay, it's really confusing for pentavalently doped. A lot of times people, when you hear pentavalently, they want to go to the P. You want to know what the memory trick is? Take a look at this. Pentavalent and trivalent. These are 2 types of materials that we have. Which one of these 2 words has an N? Oh my goodness, would you take a look at that? Pentavalent is the only word that has an N in it, therefore that is the N type of material, which means that this one over here has to be the P type of material. Okay, so we've got our pentavalently doped material, which is going to be in excess of electrons. We're going to stick a few electrons inside of this one. We're going to stick a few electrons inside of this one over here, and then we're going to stick in a few holes inside of this one. And right over here where we had this little junction, we create a barrier potential here, and we create a barrier potential here. And then we're going to go and have a base, a collector, and a emitter is what we're going to go and label some of our components. So we're going to go and just give these things a couple of titles off of these ones here. Base is going to be what controls the whole thing. That's going to be the center one here. Base, collector, emitter. Okay, so with those 3 established over here, we see that no matter how I connect a value of voltage to this, if I would connect a value of voltage across like that, we would see that I would be forward biasing this N and this P in relation to it would be forward biased, but this would be reverse biased, so it would be blocking. And then if I were to flip this battery around, just end it like that, we would see that it would then be this set that would be forward biased, but this one would be reverse biased. So we always end up with one of these that is going to go and be blocking when we're looking at our bipolar junction transistors. In order to overcome that, what we can do is we can go and take another lead, and we can go and apply that lead over to my base. And if I go and take my base, if I forward bias my base and I get actual current flow that's going to be happening inside of that base over there, what's going to happen is it is going to go and give me an opening that I can go and operate the rest. Okay, I'm just going to look at just this base over here. This is now just a P and an N type of material that have been connected together. If I go and take a look at this, I know that I've got holes on this side of the battery, I've got electrons on this side of the battery, and those electrons are going to be pushed into here. These holes are going to be created over here. We've got extra holes, extra electrons, and so overall my depletion region is going to go and sink down. Very cool, because that means that then we would be able to go and get current flow that would travel through here and over top of that small depletion region and back through. This would go and forward bias this junction over here. Now I'm going to ask you a question. Can you blow up only one side of a balloon? Well, that's an insane question. Of course you can. If you take a balloon and you actually start blowing air into it, you're going to see that that balloon, if it's a well-built balloon, is going to go and expand uniformly, right? Same thing happens over here when I start to go and establish this forward biasing. When I start to go and push holes into this base over here, they're going to be shrinking down this depletion region, but at the same time, they're shrinking down this depletion region over here. I want you to think about the base as if this thing were a balloon. So as we shrink down this depletion region to the point where it conducts, guess what? This depletion region is also going to be shrunk down to the point where it conducts as well. Which means that if I were to attach one more lead over here, that I would now be able to go and have a complete path for current flow that would go through this material over here. As long as I've got this current over here, we're going to call this my base to emitter current. As long as I've got this current that is going to be traveling through here, it is going to go and shrink down the depletion regions from my base material, which means that my overall current is also a larger amount of current is going to be able to go and flow through here. And why is that current going to be larger? Well, simply because we're going to allow it to be larger. In quite honesty, we are going to go and have a large value of resistance that is going to be placed inside of this base line over here, which is going to give us only a tiny amount of current, and then we're going to see a magnification of that current that is going to go and happen through my collector to emitter value of current over there. This is the way that we operate our BJTs and our NPN and our PNP type of transistors. PNP are just going to be all of this reversed, all of these connections reversed. And they all work through us establishing what we're going to go and call base current, okay? If we establish that base current, which is going to be a continuous loss to our system, okay, there's going to be heat that is going to be caused by this. We are always going to go and have a little bit of losses applied to our base current, but we are going to be able to go and have collector to emitter current. But we're going to go and find that there's more efficient ways than establishing this base current here. And that's what we're going to go and examine inside of our first set of videos as we get into the actual FETs and IGBTs, because FETs and IGBTs are just going to be us taking PN junctions, and we are going to go and play with the depletion regions a little more in a different type of manner to go and create conduction and blocking.